Thank you, Roger. Good morning. I have to thank Roger for accommodating my schedule, so I can get on with my flight. What I'm going to talk about is our experience just about this time last year. We did some DMT along with TDR attachment on it in a reservoir. So you have to push the button for me, huh? Next slide. This reservoir is I couldn't find one that does the job and it's all English, so I put on the translation for you. Other than Paul Mann can understand all of them, of course. This is the reservoir is in the northern part or close to the northern end of the Taiwan. It provides freshwater supply for this region, and the dam has an earth dam. It's about 80 meters high. Next slide. There's some statistics here. The dam the reservoir actually was designed by an American firm back in 1950s, Thames Consultants, a very famous consulting firm. And the reservoir started operation in 1960s. It has a capacity of about 250 million cubic meters effective storage. That may not sound like a lot for a reservoir in a large country where you have a lot of land, but this reservoir is actually probably the top 3 or top 4 in Taiwan. It's very important for irrigation, freshwater supply, less important in power generation, but when the reservoir is not functioning, there's a big problem in northern region of Taiwan. And we noticed how important it was in 2004 when we had a big typhoon, Eri typhoon. It was very heavy rainfall, much more so than what we experienced last night. 40 millimeters of rain per hour for 14 hours continuously, and during the 3 or 4 days typhoon period, it accumulated about 1,600 millimeters of water rainfall in the catch basin, so that created 700 million cubic meters of inflow into the reservoir, which more than is about 3 times the storage capacity of the reservoir. So you can imagine how fast the reservoir will have to release its own storage. Along with the water came a lot of sediment, because there was also a lot of debris flow in the upstream area. So if you look back in history, after it was completed, the reservoir would accumulate about 1.4 million cubic meters of sediment, siltation. But in that one typhoon brought in 28 million cubic meters of sediment. That accounts for about 10% of storage capacity of the reservoir. Not just that, there's so much sediment that blocked the power plant intake valve. Next page. So the operator of the reservoir was very concerned because they could not open the valve, and the water could not get in, and they could not generate power. The power generation was responsible for a revenue of $30,000 per day. So the sooner they can open the door, the better it was. And also, there was so much sediment in the reservoir, they're planning on desilting or get rid of the sediment. But the strategy of how to get rid of the sediment depends on the state of the sediment. So where do we start having this mud, and where it turned to solid or semi-solid, and eventually to a solid state, or if it is solid, how strong it is, that will be of interest to the operator. And this valve was as this big rectangular gate, 4.4 meters wide, about 8 meters long. This was built on the side of a rock slope, which fairly steep rock slope. The gate was open with a hydraulic system that has a capacity of about 80 tons. The door itself weighs 40 tons. Originally designed with a factor of safety 2, but with the accumulation of the sediment, the operator was not so sure if they could open this gate without damaging the mechanism, the hydraulic mechanism. If that was damaged, then they would not be able to open the door at all unless they drain the water out. As you can see, at the time we run the test, the water surface was at elevation 244 meter. The center of the door was at about 173 meters, so we have a 70 meters of difference in height. So they were interested about the state of the mud or sediment all the way down to the bottom level of this of intake valve. So we were called in to do the job, but they didn't tell us what to do. Of course, they didn't tell us to use DMT. They didn't know anything about DMT. So the objective of the study was to determine the densities of the mud and its distribution, how it was distributed from water, clean water, to muddy water, to watery mud, gradually down to solid soil. And also from there we can provide some idea about what kind of pressure is applied on the intake valve, and then so they can determine if that force available on the pulling mechanism enough to pull the gate up, and also in long term provide parameters for desiltation planning. How do they get rid of that much of sediment? The whole thing is supposed to be completed in 1 week. We have very little time to get all the details worked out. So we had to put something available at the time in a very short period, because for 1 day of not generating the power, they're losing $30,000 a day. So 1 week is a lot of money already. There's a big difference when you think about running DMT, if that's the case we're going to use at the time. We're either in the air or in the soil. So very clear cut. You're in the air, has no strength, and you're into something solid. Next. But in this situation, we're sort of in a gradual change from something liquid and gradually turn into solid. So that gave me a lot of headache or a lot of things to think about. How do I get around with it and still provide some useful information? The first thing came to my mind was this chart by McKetty and Krebs, 1981. Would it be nice if I use DMT and get ID and ED? Here's my density. Then I can use that to determine what kind of stress, vertically at least, it is. And then laterally with the low strength, we can pretty much expect the lateral stress equal to the vertical stress. But then if you think about it, we're probably in this region, or probably even further to the left. So we're, if this chart were to be useful, we're at least at this margin. So we got to provide some kind of safety margin in case this charge was not applicable. So that's when this TDR idea came in. TDR, if I give the full name, is time domain reflectometry, which is electromagnetic method. We generate a pulse, a step pulse with an amplitude of V0 into a coaxial cable. And then at the end, we have what we call a waveguide. When this electromagnetic wave encounter a change in impedance, in this case, we change from coaxial cable to waveguide, they generate a reflection of a wave. And that reflection, its time and the amplitude of the reflection of the electromagnetic wave tells us two things. One is the dielectric constant of the material at the waveguide, encountered at the waveguide. The other is the conductivity of the material encountered at the waveguide. The dielectric constant depends on the time difference of the reflected electromagnetic wave from the beginning and end of the waveguide. The conductivity depends on the amplitude of the returned, or the signal returned or reflected from the waveguide. So this is the key information we collect in the field, and based on this information, we can determine the dielectric constant of material where that waveguide is inserted in, and also the conductivity of the material. In order to determine the But that's only dielectric constant and conductivity. And what does that relate to? The density of the sediment, or the density, or the concentration of the soil particles in the mud. We have to do some laboratory calibration. This is the dielectric constant versus the ppm, parts per million, of the particle concentration. For clean water, the dielectric constant is about 80. For dry soil, the dielectric constant is about 5. So as the concentration gets higher, this dielectric constant goes lower. And that sounds promising from this point of view. Or if you look at the conductivity point of view, this is the conductivity of the mud that has water and solid in there, and this is the clean water. The clean water has very low conductivity, and this is the particle concentration. You can see initially you have a fairly linear relationship between the difference of the conductivity of the mud and clean water and that of the ppm. And as you go higher, close to 10 ppm, or 10 to the power of 5, then this relationship goes flat and eventually goes down. So this is very dangerous to use that, and only within certain range when you have a more or less linear relationship. Unfortunately, even with this relationship, we're looking at a range of ppm less than 1 or 100,000 ppm. Or this is the red zone we're looking at. So we're still not using the most sensitive region of the TDR. We're just putting something together in a hurry. Hopefully, together they will do the job, or at least we can solve the problem within 1 week. That was the idea. The problem with TDR, like I said, the solid contents were low towards the end, the margin where they may not work well. In order for the Ka to be sensitive, we have to have very high concentration of the solid, and this way it doesn't work because the concentration is not that high. And also we have to notice the nonlinearity between sigma, which is conductivity, and the solid concentration. The other problem we have to watch out is the isolation from the, I call it base liquid. If I go back to the previous slide, this is the sigma minus sigma W. Whatever the original fluid, without a particle, the property of that fluid itself can affect your test result. In other words, if you have a salinity or pH value in that liquid, can all affect this your reading. So in order to have correct results, you have to have a calibration of your conductivity of that liquid without the particles in there. So that's a lot of tedious process to go through in order to get the results correctly. So next one. So this is our field setup. We selected 10 test positions at about 50 to 100 meters away from the dam, the earth dam side of it. You look at the distance, you think this may be too far away from the reservoir intake, but this has a slope. There's a slope of 2 to 1. So by the time you get down to 70 meters deep, we're very close to the we're almost right next to the intake valve, and we used a barge that was available in the reservoir, which was almost like custom made for us. It was 2 big tank with a gap inside, so we can mount the drill rig right at the center and put our drill rods right through the gap and go down to the reservoir, which is 70 meters deep, and then attach this whole barge next to a dredging boat, which is very heavy. And all these borehole locations were positioned with a total station set up on a dam crest. So 10 boreholes or 10 test locations, 5 of them with TDR, 5 of them are just with DMT alone. This is the way we set it up. It was a very lightweight portable drill rig, which is quite common in Taiwan. The drill rig was not there to push things down. but just to hold the drill rod. With 90 meters of drill rod, we estimate the total weight is about 700 kilograms. So all we need is to let the rod to sink into the water and eventually into the sediment, and the dilatometer has a sharp blade at the bottom, so they'll penetrate into the sediment, and then we can run the test from the barge. This is the look of the TDR. With originally my colleague Chiping Ling was making this for a cone, so this is a sort of a dummy cone tip. Originally we were trying to fit this to a cone, so we can push the cone and then measure the TDR signals. So because we need this test, so we pull it out to fit this into the DMT, so that we can run DMT and TDR at the same time. This is the way it looked when we attach it together. Unfortunately, the first test we did, the TDR attachment was mostly plastic. You need two parts. I should go back to the previous slide. There are two parts. One is metal. This is waveguide. Then you need something that is not conductive. This is plastic, so that you create an effect of waveguide, even though the inside of it is still metal. But unfortunately, the connector here was made out of plastic, at least the first one we made. So when we use it for the first time, this thing broke at this point. So we lost our first blade, still in the reservoir, and we had to make another one to complete the job. But anyway, let's continue. This is the actual signal. TDR signal we obtained in the sediment. This is the original amplitude of the step wave we pump into the waveguide, and these are the reflected signal, and that time difference will tell us the dielectric constant, and this amplitude reflects the conductivity of the sediment. Of course, we did not use this part because the dielectric constant was not sensitive enough. We're entirely using the conductivity signals. If we collect the 5 TDR DMT signals and put them together, we started our test at about 244 meters. That's the surface of the water. And then we have one TDR measurement at about every 10 meters until we think we're close to the sediment. And then we switch to 1 meter per readings. You can see at about elevation 185, we have a clear increase of solid concentration in ppm readings, and then all the way down to about 160 some meters in elevation. This is the volume water content. This is the density ratio, which is more familiar with us. Total density divided by the density of water. So you can see it's 1.2, 1.4, at the most about 1.5. Like I said, close to the lower bound of what the Marquardian and Krabs chart will tell us. Originally, I was thinking just maybe, because I never had experience or didn't have time to verify that, maybe we can just use P0 to determine the density of the mud right next to the blade, because the mud will have a higher density than water, and then therefore creates higher stress. I just give a very briefly idea at this point. I should describe first how we ran the test. Certainly we cannot follow the standard procedure. As we lower the blade from the barge down to the water, we continuously increase the pressure inside the DMT so that we're always just slightly at a pressure lower than the P0 value. In other words, the buzzer's kind of on and off all the time, for two purposes. One is to prevent any leakage, because my air pressure is always about the same as the water pressure on the outside. So if there's any leakage, water is not allowed to come in. Next, the other advantages is I'm always calibrated. So I know, regardless of the membrane stiffness, that reading should be close to what I have, the hydrostatic pressure outside. So, and also as we entered the zone where we think we're in the sediment, we increased the test frequency, or our test was done one in every 50 centimeters or so. So this is the plot of our P0 value versus depth. This is the dashed line is the projected hydrostatic pressure. So it's fairly accurate. If you can see that the P0 value is almost in line with the hydrostatic pressure. Unfortunately, this does not agree with the TDR measurement. The TDR says at this point we have a clear increase of density. According to TDR, the clear increase of density starts at about 177 or so. Then you have a deviation with the slope. Another problem we have here is at certain level, below 170 millimeter, the pressure actually start dropping. I think we did a lot to make sure the barge does not vibrate or rock on the water surface. All the valves, the drainage valves of the reservoir were shut down. No boat was allowed in our neighborhood, but still there was a little wavy motion. I think the blade was kind of moving a little bit inside of the mud that creates some kind of cavitation, and that caused the P0 and P1 actually decrease with depth beyond a certain level. But again, on the positive side, I think this is because we're into something quite solid. So when you push it and then move away from it, the pressure does not come back immediately, and that creates some kind of cavitation. So the idea, if I were to use this in the future, even in this case, I assume when the mud is soft enough, the undrained shear strength or the friction angle is 0 for mud, a very diluted case. So P0 in this case should be equal to sigma H. And sigma H should be equal to sigma V, because there's K0 equals to 1. There's no strength. And from there, I can estimate the total density of the mud according to the slope of the P0 versus depth. The reason we do not have enough sensitivity is because this is if you notice the previous 5 sets of curve was from the DMT only. This is a DMT TDR, so they're all very similar. They all have the similar results. The clear deviation of the slope away from the clean water did not start until about 177 meters, not like TDR, which is 185 meters. We are off by about 10 meters or so. It's because I could not, at the time, my setup did not separate the water pressure. If I had the chance to do it again, I would probably flood inside of the dilatometer, not with water because it's conductive, but with some kind of oil, as Silvano suggested. That will offset the effect of water, and that will increase the sensitivity. So maybe without the TDR, I will be able to do this job just by DMT alone, because I think using the DMT alone has a lot of advantage, because this is the experience I learned. DMT is very simple. There's nothing you can go wrong with that, even in 70 meters of water, unless you drop it. But it does not have the sensitivity at the time, because I did not isolate the water pressure out. I did not use what I should call it the differential pressure. That'd be a better way to call it. But the sensitivity of TDR at the time just had enough, but barely enough sensitivity to do the job. Now, according to our test data, we did some calculation. It took about 90 tons of force, a little more than the original design capacity to pull it out. They opened the valve, but it was open according to, based on our test, it was open safely, and the power generation started, so everybody was happy. But I think if we were to do this in the future, and there's a very good chance we'll do it in the future, because the reservoir has a lot of sediment problem, and that's not the only place we have to worry about getting rid of the sediment. So I think a differential pressure to measure P0, in other words, P0 is not against air pressure. The p knots against the liquid pressure inside of the dilatometer. I think that will make a significant improvement. DMT has the advantage of relationship to the stress and density state, which is very important. I think certainly TDR cannot do it. TDR can only relate to density. It has nothing to do with the stress. So, and also, TDR requires a serious calibration. The calibration is not for stress kind of calibration, but it's for conductivity kind of calibration, which is quite tedious and very sensitive. And also, I should mention, use TDR, you need a coaxial cable, which is 1 centimeter in diameter. You cannot thread that inside of a drill rod. So to do this, fortunately, we're in the reservoir. We can thread it outside of the cable or the drill rod and lead it to take it to the barge. Otherwise, we will not be able to do it if we're in an online situation. Once you push this thing in the ground, it will damage the cable, and that should take care of my presentation. 25 minutes, isn't it? Don't forget this. This is my main reason to be here. Thank you.
The Bradford No. 3 Dam has for over 100 years been impounding the flows of Marilla Brook to create a water supply dam, a 20-acre lake that furnishes water to the city of Bradford, Pennsylvania, as well as recreational opportunities in the form of fishing, canoeing, and hiking. The dam is located in north central Pennsylvania, a few miles south of the Pennsylvania line. The reservoir is located in the highlands about 4 miles west of the city of Bradford, in an area that is part of the Allegheny National Forest region of Pennsylvania. This is a locality where the soils are not particularly thick. They're generally less than 20 feet, and they are generally not soft. They are, on the other hand, generally containing stones and rocks. So generally speaking, this sort of a terrain is not amenable to use of the dilatometer. The Bradford No. 3 Dam was designed and constructed by William Hanley, who was a local contractor in the Bradford area. He was primarily a building contractor, and he constructed the post office and certain other buildings in the area. He was not a dam specialist by any means. The dam was placed in service in 1900, and it's been owned and operated by the Bradford City Water Authority during that entire period. The dam is classified by the designation B1 High Hazard 1 Dam. The B1 is simply meaning that the dam is over 40 feet in height. The High Hazard 1 designating that should the dam fail suddenly, one could expect the loss of life and severe economic consequences. The dam is 47 feet high, 770 feet long. The face slopes of the dam are quite a bit steeper than one would expect with a modern, in a modern day dam. The downstream slope is 2 to 1. The upstream slope is 2.5 to 1, steepening to 1.5 to 1 in the top 8 feet. The spillway is constructed of stone masonry, and the outlet works consist simply of some cast iron pipes that extend from an upstream inlet through to a discharge point on the downstream side of the dam. This is the design drawing of the dam. The entire design was committed to one piece of paper. There are no calculations whatsoever. This is the dam cross-section, of course, and this is a plan view showing the spillway on the near the left abutment. This is what's called a diaphragm earth dam, the diaphragm referring to a masonry block wall that was constructed at the center. It's 6 feet wide at the bottom, narrowing to 2 feet at the top. The base of this diaphragm was constructed 9 feet below the general base level of the dam. The central part of the dam, the core, is 60 feet wide at the base, narrowing to 12 feet at the top. According to this drawing, that core was constructed of select material. There is no specification extant that would describe to us what that select material is. The shell of the dam was constructed of random material. As a later investigation showed, there's no perceptible difference between the shell and the core. You'll note that this dam was not provided with a chimney drain, a blanket drain, or a toe drain. So one might expect that over a period of time, one would see manifestations of seepage on the downstream slope, and in fact, that's what's happened. There are several issues that require attention on this dam. One is that the spillway was undersized, as is the case for many dams of this vintage. In the case of an extreme storm event, one might expect that the dam would be overtopped with the consequence of a breaching failure. Also, the stability of the embankment had never been documented. There is no record that any soil testing was ever done. No strength parameters were ever determined. No stability analyses, Bishop or whatever, were never done. Thirdly, the outward works are unsatisfactory by today's standards. The valves that operate the drawdown pipe and the water supply lines are located downstream of the dam, so that in the event that these valves had to be closed, one would have a pressurized condition in the pipes beneath the dam, and that's not acceptable. Lastly, again, there are wet zones that were seen on the downstream face of the dam, due no doubt to the absence of proper drainage measures on the downstream shell area. And along with the wet zone, there have been found locations of localized slippage on the downstream face of the embankment. This is a shot from the spillway area. Again, you can see that the downstream slope is pretty steep. This is the spillway area, and that's the valve control area on the downstream side of the dam. This is the downstream face near the base, and you can see some undulations in the face of the dam and some dark areas that represent locations where seepage is exiting and where there's been a little bit of slippage. All of these points clearly warranted a subsurface investigation be conducted of the dam. A series of test borings were drilled from the top of the dam and from various points on the downstream slope. As is customary in this part of the United States, the test borings were drilled through the embankment and 15 to 25 feet into the foundation materials, which were alluvial. Standard penetration tests were conducted on a continuous basis. Pocket penetrometer values were taken on soils that exhibited cohesive characteristics. Shelby tube samples were collected of selected intervals, and laboratory strength tests were conducted on these samples. We used a direct shear test for that purpose. In addition, piezometers were installed in the dam to determine the groundwater levels. This shows the investigation in progress. There's very little room, obviously, on the top of the dam, and this was about the smallest rig we could find for this purpose. This shows the drilling program in progress as well, with one of the piezometers on the downstream shell. The drilling program had not been underway for more than 2 hours when I got a call from our field geologist indicating that he was alarmed by what he was finding in the first boring. And he described to me a condition where the standard penetration test values were rather low. They were 10 or less, and there were some intervals where the drill tools sunk under their own weight. In other words, the end value was essentially 0. That first boring we pulled off of, we backfilled the hole, and we stepped back and considered what the implications were. We then, the following week, proceeded with the drilling program once again, drilling additional holes along the top of the dam and along the downstream face. This profile is representative of the kinds of penetration resistances we were finding through the dam embankment, and clearly the alluvial foundations exhibit good strength characteristics or densities, but the materials through the full height of the dam were less than one would hope for a structure that's impounding water. Pocket penetrometer values taken on the materials that exhibited cohesion showed a profile of this type, and generally speaking, the materials exhibited a estimated undrained strength value of less than 0.5 kips per square foot, and admittedly pocket penetrometer values are crude, but they did give us an initial indication at least of what the undrained strength might be. Generally the material is soft, very soft. The objectives of our stability analysis were first to determine the stability of the embankment as it stood, and secondly to form a basis for the design of other stabilization measures such as a buttress, which we fully expected would be needed in order to achieve satisfactory factors of safety. Also, we had to we're interested in doing effective stress stability analyses to determine how much the reservoir pool had to be lowered to achieve a satisfactory factor of safety while the design measures were being developed. It was not feasible or reasonable to entirely de-water the pool because of the presence of the fish population, which the Water Authority wanted to, and the Fish Commission wanted to maintain while the design was underway. The Pennsylvania Division of Dam Safety requires a factor of safety of 1.5 against failure of the downstream face under conditions of steady state seepage in a normal pool condition. The effective stress stability analysis we conducted, Morgenstern-Price method was used. We computed a factor of safety of 1.84, which was immediately seen to be implausible. And this was based on laboratory strength tests that indicated friction angles of between 33 and 37 degrees for phi and cohesion on the order of 0.5 to 1.3 KSF. These laboratory strength values were attributed to some sample disturbance, but primarily to a probable sampling that was not representative of the intervals we were shooting for. And just as a matter of quick comparison, we did a total stress stability analysis using the pocket penetrometer values, and we got a computed factor of safety of between 1 and 1.2, which seemed to us to be more reasonable, although total stress analysis was not sufficient, obviously, for our purposes. Our conclusions from this initial investigation were that for a traditional subsurface investigation of the type we conducted using Shelby tube sampling and laboratory testing along with standard penetration tests, that sort of an investigation yielded unreliable and or contradictory estimates of shear strength and factors of safety. And we concluded that more sophisticated in-place testing was required. For that, we called in Roger Fail-Metzger, and he was able to conduct a supplementary investigation that involved dilatometer soundings and borehole shear tests. The dilatometer soundings were conducted in precisely the same way as you saw them conducted yesterday. I won't go into any detail. These are some of the ones that were done from the top of the dam. Next. The dilatometer soundings yielded some interesting results. First of all, it was clear from these soundings that the dam had been constructed of alternating layers of essentially cohesionless material and cohesive material. The cohesionless are denoted by the yellow color, and the darker brown or tan are the cohesive. So it was cohesionless, cohesive, back and forth from top of dam down to the bottom. Same sort of profile was found in the other holes. It appeared, on the other hand, that there was not any particular strong lateral persistence of the layers from one sounding location to the other, which may help to describe why, when we collected Shelby tube samples in the initial investigation, whereas we went down to a proper depth and then bored a supplementary boring to get the Shelby tube, we may well have been in a different material than we had expected to find. The dilatometer was certainly very good in delineating these various layers. This is a photograph of dam construction in 1898. You'll recognize the spillway over here, the intake down here. The top of the dam was nearing completion. And we see that the construction was being undertaken by use of mule and horse-drawn wagons to haul the soil from the borrow area and place it here, and also there is mule-drawn grading equipment that was used to smooth out the material. We are speculating that the reason for the alternating cohesionless and cohesive layers is due to the fact that the dam constructor, Mr. Hanley, wanted to put down a layer of cohesive material to get as low permeability as possible, but in order to traverse the site and allow the wagons to pass over the cohesive material, he had to put in a layer of cohesionless material as a rudimentary pavement. So we get cohesive, cohesionless, back and forth, and that, I believe, describes how this dam was constructed and why we have the layering we do. The dilatometer soundings also provided us a profile of the undrained shear strength with depth. The undrained shear strength was generally less than 0.5 kips per square foot, which places the material in the very soft to soft category. And this dilatometer profile of undrained shear strength was very similar to what had been anticipated on the basis of the pocket penetrometer values. The dilatometer soundings provided us as well with a profile of the effective friction angle. These individual values ranged from 27 to 42 degrees. The mean value was about 34 degrees. In order to get effective strength parameters for the cohesive layers, we had to turn to the borehole shear device, and this is a tool that had been developed by Dr. Richard Handy at Iowa State University. This is a photograph of the platen system that goes down to the hole. The platens, in fact, are here. A lateral pressure is applied to the hole, and then this device is tugged up the hole to get movement and develop each of the 5 points for a given test. Next. And this is the instrumentation at the collar of the hole. And this is the readout equipment. The borehole shear devices provided a rather nice more envelope for the cohesive materials, and the tests at various depths were clustered together on this plot, and we find that the overall friction angle is about 20.7 degrees in cohesion, near to 0.2 kips per square foot. In order to conduct this revised stability analysis in light of the layered nature of the material, I decided that a reasonable approach here would be to take a weighted average strength. So given that the cohesionless materials represented 44% of the material on average, it seemed, and the cohesive about 56%, I took a weighted average of the individual strengths from the cohesionless and the cohesive materials, and I computed an operative strength, shall we say, of a phi of 25 degrees and C of 0.115 KSF. Went through the effective stress stability analysis, and I determined that the factor of safety of the existing embankment is on the order of 1.05, which is intuitively what I would expect it to be. In conclusion, in assessing the stability of this dam embankment, the customary field and laboratory methods that were initially employed, the standard penetration test, pocket penetrometer values, Shelby tube sampling, and laboratory testing, in this particular instance, produced results that were contradictory or unreliable. More sophisticated in-place testing involving dilatometer and borehole shear testing proved invaluable in determining the stratigraphic and strength parameters that were essential to conduct a reasonable and meaningful effective stress stability analysis. Dilatometer and borehole shear testing are not in common use in projects of this type in northern Appalachia, largely because of the nature of the soils there. But the future use of these tools is certainly recommended in instances such as I faced here when the usual methods of soil characterization prove inadequate. Thank you.
Actually, I'm making this presentation on behalf of the authors. For some reason, they could not attend it, so I'd like to just take this opportunity to show the effectiveness of the dilatometer in this project. I did some data analysis for this project, so I'm not totally blind to the scope of this work, hopefully. This project is located in Massachusetts. It's the relocation of Route 44 between Plymouth and Carver. The stretches of the new highway span existing cranberry bogs with a lot of organic materials. The material probably has a thickness of 10 meters, that is 30 feet. And the design team chose to use the sheet piling and mechanically stabilize the earth walls for the cranberry bog crossings. And they will also just replace some of the peat material to just stabilize the roadway base. This is the typical highway cross-section. This is the cross-section view. You can see this is the center line of the roadway, and this was the ground surface of the bog area. And this is the bottom of the bog area. So the total thickness was probably 10 meters. And this material was supposed to be replaced with backfill after the sheet pilings were driven to the design depth. And you can see this is the roadway, has probably width of 90 feet from side to side. And the sheet piling has probably distance of 150 feet from side to side. And the construction just, actually we got some idea of the procedures the design team will just carry on. First, sheet piling will be just installed along both sides of the new alignment. And the organic materials was supposed to be dredged out and replaced with probably 30 feet of granular fill. But there's one condition that is very challenging to the compaction of the new road base. That is mostly the underwater construction was under the way, so it is really very challenging to compact the material. So the compaction level of the granular fill was not reached to the design level of modified Proctor of 95%. Later just left some of the concerns of liquefaction due to the design team's analysis of the liquefaction potential. So deep dynamic compaction was used for the mitigation of the liquefaction hazard. This picture was taken from one side of the water. This is the one side of the sheet piling after driven into the place. And this open water was supposed to be drained down, drained down to the design level, and also the bog material will be just replaced with granular fill. As you can see, here's the construction that is going on along one side of the sheet piling. Some of the materials were just dropped just on the water and let it to just settle down by itself. Yeah, this is another picture showing the construction that was going on the site on one side of the sheet piling. Yeah, again, showing the construction, how the material was just dredged down to the design level and just moved out of the site. As you can see, at this level, the bog material was just excavated and replaced with some granular fill. But at some time, the water level of the bog was really high, so the placement of the granular fill was just totally at the luck of the water level. If it is high, so just dump it into the replacement area and let it settle by itself. If it is low, so the bulldozer will be was used to just sort of compact some of the locations. Yeah, you can see the bulldozer was used to spread out some of the granular fill. So the construction of the road base was in the challenge condition. So the deep dynamic compaction was used by the design team. The deep compaction temper was chosen at this level. It has a weight of 14.5 tons. And the height of the temper was probably 3 feet. And the cross section has a diameter of probably 5 feet. This is the construction of the compaction on the site. Actually, there are two drop heights for this construction. One is the 60 feet pass of the drop height from the center line. And another drop height was 1/2 of it. That is 30 feet between actually the sheet pilings and some of the distance from the center line. And this design was just chosen because there's some concern that the drop of the weight of the compaction will just affect the sheet piling because some of the generated lateral stress may push the sheet piling towards the water, so may just get some excessive displacement on the two sides. This was some of the concern of the design team. But unfortunately, there's no sensors or devices installed along the sheet pilings. So right now, there's no actually quantitative data to back up this concern. This is only some of the things that the design team chose to do at the time. And over the majority of the site, actually the two passes were just completed on the two passes level. First, they just did the one pass of the compaction, and then in between the locations, they inserted another round of the compaction. This is the plan view of the typical layout pattern. As you can see, this is the center line of the roadway, and this is one side of the sheet piling, another side of the sheet piling, and the solid dots are used to show the one pass of the drop procedure. As you can see, the practice actually was like this. They would first drop the temper at these locations, and then after they finish up this one pass of the drop, they just start with another round of the compaction. And also, as we just mentioned, they choose to use the 60 feet drop compaction in some of the areas that is very close to the center line, and then they just have the reduced drop height at some of the areas very close to the sheet pilings. Yeah, this is a picture showing the compaction. Actually, they just carry out from one side of the water and then move on, and then they just back and forth to just finish the first round and then insert the second path of the compaction. They choose to use the maximum of 9 drops at each of the grade point location, but they just reduce the drops at the crater depth if the footprint is larger than 5 feet. And also in some instances, numbers of the drops and also the drop heights were just also revised at the locations very close to the sheet piling. Still, that was a concern of some of the effect on the sheet pilings on the two sides. The design energy for the compaction was just selected by using this formula, by including the concern of the temper, weight, drop height, number of drops, and also number of passes. They used the Lucas 1995 formula to estimate the depth of the improvement. From this formula, the design team just estimate improvement zone of probably 15 to 20 feet. But in the end, we'll see probably this is a little bit conservative in considering using this formula. They reached probably 20 to 25 feet of the compaction, effective compaction depth. So as a QA and the QC practice, they just did the pre-densification testing and also the post-densification testings by using the both the CPTs and the DMTs. But here, they just will just focus more of the DMT results. The objectives is to provide baseline data to just see the original soil profiles, and also after the densification, they will just compare that with the baseline data to see how much improvement was achieved after the compaction. Could you just hit the key? Probably there's something, yeah, and just hit down, yeah, and also, yeah. This is a figure showing some of the results. Actually, from the DMT soundings at some selected locations, they choose to just present the data very near to the sheet pilings, and also they did some of the testings along the center line. And from the testings with some of the unfortunately findings after the backfill of the granular material, they found still there's some organic materials left very close to the dredge line. But at the time, there's nothing they can do. The only thing they can just expect was actually the densification will also help to just improve the strength or the stiffness of the organic material. But later on, we can see there are some very interesting results showing up in this zone also. And just one bit, okay. And also, if you follow this solid line, you can see actually the data showing very consistently for this zone that is probably 5 feet thick regarding the location. Yeah. This is a CPT profile they used. Actually, the thing they want to just show up is actually the organic materials very consistently get profiled by the CPT, the same thing as the DMT. Yeah. Probably, yeah, one more key. Yeah. Yeah. This is the comparison before and after the densification showing up with the DMT data. This is a location very near to the sheet piling at this station. And you can see the solid symbol is used as the baseline, and several other soundings showing up with these symbols from this line, the second to the end, as the post densification. It appears like the upper probably 5 to 10 feet of the zone underneath the ground was the zone that was improved significantly by this practice. And for the zone that is a little bit deeper was improved, but not as much as expected. And for this small zone where organics was still on the site, it just did not show very consistent improvement, because some of the locations was just even probably loosened or just disturbed further, so that the strength was not very significantly improved, or even just lower. Some other locations they got achieved higher horizontal stress. Oh, yeah. One back. Sorry. Yeah. This is another presentation. Actually, the same location, the same sounding group, but showing up as the constrained modulus. Yeah. If you just look at this zone, it is still very inconsistent regarding the improvement, but still at the shallow depth appears like a lot of improvement going on. Yeah, this is the comparison by using the CPT data. It appears like the compaction achieved very good design level from the ground surface to probably 10 feet. And also there's a mixed zone showing up at the organic layer. The authors concluded that the DMT and the CPT both are very excellent tools for providing the profiles of the soils. And for the QA and the QC practice, it appears like they can just provide some very good results to just for the analysis to see if the design compaction was achieved. And actually, there's no quantitative results showing up in this presentation, but in their article, it appears like there's some quantitative analysis regarding the constrained modulus. Also, the constrained modulus of the DMT appear to be a little bit more sensitive to the densification effects. So it was concluded that the DMT sounding may be a better choice. And the constrained modulus values indicate that lateral movement of the sheet piling during the compaction just reduce the effectiveness of the deep compaction, probably due to some of the lateral movement of the material. But this was not exactly analyzed with the focus. So at this point, there's no conclusive points there yet. Again, it appears like they achieved some deeper densification zone than expected by using the Lucas 1995 formula. The zone of the maximum improvement may be slightly deeper, but it is not quantified with some definitive comparison. So they only just qualitatively reached this remark. And they want to just thank the organizations and the firms listed on this slide. And thank you. That's all I have.
My talk is going to discuss 5 case histories where we redesigned somebody else's work. Somebody was the first investigator, recommended something that was much too conservative based on SPT results and limited laboratory test data. We went in and did DMT and showed that the applied bearing pressures could be doubled and tripled and still achieve settlements that were tolerable. Okay, I'm going to talk about the pitfalls of SPT and CPT for settlement prediction, and then why the DMT, which is really a calibrated static stiffness test, should be used instead. And then I'm going to show the results of the 5 case studies. This is something we talked about a little bit yesterday. You know, the benefit of the flat DMT is that it's measures the stiffness in the operative level, where the strain levels where the buildings and embankments would apply that type of strain to the soil, as opposed to geophysical tests where you have to extrapolate back to a modulus in that strain range, and penetration tests which fail the soil, and then you have to come back to that strain level. SPT for settlement, part of the problem is really the test itself. The hammer energy, it can range anywhere from 30 to 95% of the theoretical potential energy. It depends on hammer type as much as anything, very operator dependent, and even though the test is done all the time, it's rarely calibrated. There's also a significant amount of measurement noise, test repeatability. You can have just errors more with the safety hammer and donut hammer, where you have the operator is more important in the energy delivery. For example, if you get an operator that gets drunk the night before, he comes back hungover and he's hardly lifting the hammer at all. And then you get the next day, he gets mad at his wife and bangs the hell out of the hammer. So you can get a lot of error just in measurement. And really SPT is a non-calibrated high-strain dynamic test. And we're trying to model what the static deformation characteristics are of the soil to figure out settlement. Next. SPT has changed quite a bit since the 1940s, but isn't recognized by very many engineers. The automatic hammers deliver, they don't have the ropes, there's hardly any losses in those. They can deliver up to 55% more energy than safety hammers. Also, another fact is that the early days the ID of the barrel was the same as the tip. Now it is larger to accommodate liners, but liners are rarely used, so any friction that would have occurred along the barrel is minimized by not using liners. Thirdly, the hollow stem augers, they remove all the existing geostatic stresses versus mud rotary drilling, where you at least have the weight of the fluid acting on the soil. If you factor all those things in, today's N value can be half of what a 1940 N value would be. So there's a need to correct today's N value to N60 values. Skempton wrote a paper in 1986 showing us how to do that, but I've looked at a lot of boring logs and I never see that. You just get the raw values. So that correction could be quite important, considering that your value could be half of what a 1940 value would be. Yet many people use the old charts developed by Peck and Terzaghi as, you know, just the way it is, and never make that correction. This is a chart showing the best case scenario, correcting your N value to N60 values and trying to predict settlement and sand. The formula for Berlin and Burbridge is in the paper, but it shows just a considerable amount of scatter under the best case scenario for prediction of settlement in sands. This method has a coefficient of variation, which is the standard deviation divided by the average value of 0.67, which is, this is a huge number. Duncan, in his probability paper in 2000, showed just with the error of the method alone of predicting, you needed to have an average settlement of less than or equal to 0.3 inches to be 95% assured that your maximum settlement wouldn't exceed an inch. So that's, and then my discussion of Duncan, that average will even be considerably less if you consider test variability and subsurface, test repeatability error and subsurface variability. So you could be, you know, you might need an average value of 0.2 inches just to be assured that your settlement will be less than an inch in sands, and then after you correct for N60. We looked at this a little bit yesterday. You know, what factor do you use to multiply to get a modulus from cone resistance? You have a range of tenfold. Next. Okay, the benefits for the DMT for settlement computation is it's a calibrated static deformation test. It's performed at the operative strain level and at close depth intervals. I mentioned it earlier in the panel discussion. If we encounter, my practice is if we encounter a soft layer, we'll do additional tests to get even, do them at 10 centimeter intervals versus the normal depth interval that we use is 20 centimeter intervals. So if you get a real soft layer, you can do extra tests as part of the process to better define a soft layer, which could be critical to your design. The case study database, which is studies done by Dr. Schmertman and Jack Hayes, showed, if I combined them all, I had an average predicted to measured value of 1.06 and a standard deviation of 0.18. I threw out, in my assessment of these values, I threw out the ones where there's one or two where the DMT was driven, because I never do that, and there was some sensitive silts that I threw out because we don't encounter them. But if you throw those out, that you can get a value that low. Next. This is their database. The darker red line is the one-to-one line. You can see how closely the measured values match the predicted, or the predicted values match the measured values. And this is for all soils, not just sands like we showed on the SPT chart. Okay, these are the case studies. I'm going to look at today. Let's see. In general, let's see, the first investigator, you know, he had high settlements. This one, 1 to 4 inches, 2.5 inches, 3 inches, 3 to 5, greater than 1. All were unsatisfactory, and yet the bearing pressures that they had done their analysis were relatively low. We went back in, did DMT, and showed that we could use higher bearing pressures and get lower settlements, and our predicted settlements were much lower than theirs at higher bearing pressures. Next. Here's the first study. We found that, let's see, this one here, we went from a bearing pressure of 1,000 PSF to 1,500 PSF, and our settlement predictions were less than an inch. We went in, did the our holes adjacent to the 2 worst holes that the first investigator had encountered. They were worried about this clay layer down here, and from the DMT we found that it was at least lightly over consolidated, and the stiffness values were quite reasonable, and settlement wasn't as large as they expected, up to 100 millimeters of settlement, and we were showing less than 25. Thanks. This is an interesting site. There were really 3 parcels of property here. One was the Walmart store, the middle one was a Home Depot, and the other one was a giant food store. All 3 had the similar geology because we tested the Walmart store and the giant food store. In here, it again has fairly decent constrained modulus, and the soils are lightly over consolidated. We found similar conditions at the giant food store. At the Home Depot, which have similar loads, we didn't do the investigation, but the designer recommended stone columns, and it cost the Home Depot people an extra $750,000 for stone columns that they most likely didn't need. Next one. This was at the Walmart store. We wanted to prove how well the DMT was doing, so we did an embankment load test where we applied a certain surcharge that would model the footing and measure settlement. There was the clay layer down there. We had predicted with the DMT anywhere from various spots along the site from 1/4 inch to 3/4 of an inch, and with this embankment load test we found 1/2 inch, and we had some piezometers in there. It drained so rapidly that you couldn't even read them. They just were, no excess pore pressure occurred, so we felt that this was a good model and showed that the DMT was predicting the settlement accurately. Next one. This is another project where first designer thought that he was going to get 3 inches of settlement. There's some softer areas down a little deeper, but when we did the analysis, we showed that you could bump the bearing pressure from, the original designer had 3,000 up to 5,000, and we're showing less than 1/2 inch of settlement. The material's all, again, at least lightly over consolidated to a little bit better than that. Next slide, please. This is what the building looks like today. It's a beautiful looking building. There weren't any cracks. I took this photograph late last week. It's perfect, shows it works. Next one. This project was in Detroit. The original designer was worried about these clays, and we show them to be at least they're over consolidated, and they don't have stiffness is pretty good. They had recommended a matte foundation, and we're predicting 3 to 5 inches, 75 to 125 millimeters of settlement for the load and bearing pressure of 2,000. We bumped it up to 4,000 PSF, and we showed less than an inch of settlement at all the spots. Building's performing fine. Next. This site was pretty interesting. This was in Chicago. The first designer recommended about 2,000 PSF bearing and showed over an inch of settlement. There were a few soft areas out here, but we picked them up with the DMT and did extra tests and found those areas. And it was recommended that those areas just be excavated and replaced with controlled fill. But the rest of the site was pretty good. So I think what happened, the original designer saw a couple of the soft areas, got scared, said, oh, it's not going to work, and was uncomfortable with the design. But the DMT, because it's such close interval spacing, was able to pick up those soft areas. You could effectively remove them and replace them with controlled fill. And after we did that, we recommended, instead of 2,000 PSF bearing pressure, to use 6,000 PSF, and we had settlements less than an inch. Next. Okay, my conclusions for this paper really are that I believe today engineers' biggest mistakes are recommending costly foundation solutions without adequate data to prove that that solution is really needed. There's no point in recommending piles or ground improvement unless you're absolutely sure that they're needed. If you're not sure, you need to do more testing. And I think DMT is an excellent tool to figure out really what you have. It's my opinion that standard penetration test data should never be used to predict foundations settlements. It's just way too inaccurate. The probability of that material, you have to predict something, have an average settlement of less than 0.2 inches to be sure that you'd have less than an inch of settlement with any confidence. And CPT really isn't a whole lot better. It has such a wide range of what factor to use to even get modulus. And I think both these tests suffer because they're performed at such high strain levels that it's hard to extrapolate back to a modulus value at the strain level that the building will impose on the soil. And I believe accurate settlement predictions can be made using dilatometer test data. In the case studies, we've shown that you can greatly improve your design and the performance will be adequate and the building will perform as intended. Lastly, the dilatometer is not an expensive in-situ test, and appropriate interpretation of testing data can save quite a lot of money in the foundation design as presented in these cases.
Hello, everybody. My name is Marcos Arroyo. I'm presenting this work that I co-authored with Teresa Mateos. She's not from my department. She's from an engineering firm in Madrid, Iberinsa. I will first describe a little the project, then give some details about the prediction method that we employed for this, the problems posed by the project, then show you some monitoring results, and then try to conclude. So this is the airport of Barcelona. It's called El Prat. Has 3 runways. The third one has been recently built, and now they are building this new terminal here. This is the old terminal. The new terminal is rather bigger than the old because that's meant to be, well, a success. So they need new accesses for this terminal, and that was the area where they had to put the new motorway. This one, that's the old motorway, it will be put into that area, and then a branch will go to the new terminal. This is a heavily built area, so this 8-lane motorway access has to crisscross over a lot of infrastructures, to waterways, to highways, a railway. So the design called for a a large quantity of very high embankments which were located very near newly built or existing structures. And this is a typical sheet from the geotechnical profile of one of the motorway axes. And we are here in a deltaic area on the Mediterranean. And the overall structure has 3 layers. You have at the bottom, this is like 50 meters, I believe, from zero. Those are this is the zero given by the sea. So we have the water just there. At the bottom, I was saying, you have the a gravelly aquifer that you cannot perforate with piles, because it's the only remaining source of water really for the city or the whole area of Barcelona. So in the middle you have a layer of clay, silt here, and on top of it you have sands. So this is a structure. Those sands are, well, we will see more of them later on, but they are fairly good, apart from in some places where someone has been so clever as to sell the sands, then sell again its place as a well, for fill, for people to dump trash in there, and then sell it a third time for someone to build a motorway on top of it. So that was one of the possible difficulties that we encountered on the design. Another one was this gray layer there, that I will go back to it, which was in the middle of the silt layer, but it was extremely soft, or at least it appeared to be. And this is the outline of the motorway, very high, about 10, 12 meters of large embankments and crisscrossing with structures, as I was saying. So I cannot enter really into the details of the soil investigation, which was included, well, quite a great number of soundings, and then of course CPTU and of course Dilatometer, otherwise I won't be here. I was just to point a couple of things based only on Dilatometer results. This is the average ID of all the Dilatometer soundings we made on the area, and it's interesting because you see here a little bit of clay sometimes appears at the top, then you have the sands, then you have the transition to the lower clays, and sometimes some more sandy strata might appear there. So you have here a good picture of what is the general structure of the area. Of course, the detail of every single sounding is more noisy, and sometimes the transition is more abrupt, etc. Another picture that I found interesting was the KD. The KD on the sands was sometimes rather high, and discussing with the geologist, they weren't able really to explain me why it should be like that, because their estimates of OCR for that sand was really low. I have sometimes thought that it might be related to the high or relatively high carbonate content that we have in the area, but I don't really know, because other people here have suggested also that desiccation might play a role. Well, that's okay. So now let's go to the prediction method there. Well, just summarizing the design situation, we have well, as general constraints, high water table. We did expect large settlements from previous experience due to the silts and muds and clays below, and also because those embankments were really large and they were going to load onto the lower layers. Also, there was another problem, that the field to build the embankments was really scarce, so that added to the tightness of the schedule. You have to count that the field that was maybe used to preload had to be recycled to be used again as embankment on other areas. Piles for foundation of structures were problematic for these reasons of aquifer contamination. And of course, the project started behind the schedule. So the local characterization practice there in the area was characterized, well, has these traits. So you have a poor sampling practice. SPT is very common. CPTU and pressure meter, Menard type, has been introduced since 15 years ago, but there was no experience at all with DMT. There were some interesting local design successes in the area that had been based on preloading tests, large preloading tests, but they were embankments always below 4 meters, so about a third of the height that we were interested in. So we had to make some design choices, and we did agree that a certain amount of preloading was a need for ensure that the structures won't move when we built up our embankments, and also some preloading might be needed to accelerate settlement in some of those embankments just to get again into a schedule. Well, we decided to skip the load test phase because that will we didn't really have time to do a 12-meter high load test, so we decided to rely on monitoring. And of course, we were employing the basically we did rely mostly on in-situ testing for the whole design, because we knew, and then it was the case that recovering samples and trying to design that on the basis of laboratory tests was going to be really, really difficult. And the two basic formulas for all the settlement calculations are this one, the one-dimensional integral proposed by Professor Marchetti, and then you add there the one-dimensional consolidation theory of Terzaghi. Go ahead. Of course, however much we were convinced, we had to convince other people that that was the correct way to address this problem. So we had to present some results to establish how sound was our approach. First thing, we took some with rather difficulty. We managed to do some odometers, and the tangent moduli there was not very far from the average moduli of recover from the DMT. So that was one argument. That was not enough. So fortunately, we had this nearby load test, only 4 meter high, but in which they didn't have done any DMTs, but they have a CPTU just right in the middle. So we were able to relate, because we were doing both kind of tests. We were able to relate the CPT and the DMT and the dilatometer, and so as to extrapolate and to back predict that load test that had already finished. And the result was rather good, as you can see here, by comparison with an extensometer that has been placed on that load test. Just as an aside, I have mentioned that we had to establish a correlation there between QC and the dilatometer modulus to predict the load test performance. We had to we were at the beginning misled by trying to relate directly our paired measurements of QC and M, what I call here a classical regression. That didn't work. We had to approach it differently. I tried to relate them on obtain this alpha on the basis of a settlement evaluation, on a performance-based correlation, I will say. There are more details there if you're interested in that. Now let's see how this thing is going. That's the situation today. I don't know if you can see the photograph there, but this is a truck up some. This is up one of these embankments, and they are retiring some preloading from a structure there. This is what is meant to protect the instrumentation. This is also an aerial view, and you see here all the embankments being built, or part of them. So most of the preloadings have finished already. The embankments are still being built, and fortunately some instruments are still surviving. So I brought you here just 3 cases, but we hope at the end of the work to have quite a few more. This first case is what I call this, has a standard delta profile in which you have the sands on top and then move to the clay silty layers. We have 3 preloading embankments on the area where this DMT was made, and they were high but moderate size by the standards of the works there. And this first case, the results have been excellent. I mean, this is the predicted settlement. Well, I have to say that when we make the prediction, we had to throw in some secondary consolidation for good measure, because it has someone like it, and but then this prediction is without this extra bit, because it has been clear since the measure has begun that no secondary consolidation really takes place there. Even, of course, when we made the project, we didn't knew what was going to be the proper schedule of building up those embankments. So the predictions in times of we did some with instant loading, then and others with other rates. But the point here is that when you actually have the load history, and you try to follow that with doing kind of convolution of the loading, even the rate of development is pretty much accurate in that case. Go ahead. This is a second case. This is a permanent embankment, the same height. It's a little bit longer and has risen very, very slowly. I think that it's not yet 12 meters. It's about 10 meters now. The characteristic thing here is that it has a very soft mud layer just there below the sands, that gray thing that was on the drawing beforehand. And here the results have been less successful. This is the load history, and this is the plate measure settlement, and it was going relatively well. But then the prediction at this point is an overestimate, really, and we have still to find out exactly what was that. But our suspicion now by other this is not at the same moment at this of this measure. This is one extensometer that then went broke at some moment. But we did some comparisons, and our impression now, this is what we predicted, was that we did really overestimate the deformability of this soft mud layer for some reason. The third case was one of these patches of land where the owner had sold the sand and then well, fill it with made ground of variable thickness, and there on, well, it was very variable all along the this stretch of land, and the DMT readings failed, of course, because it had everything, gravels and not gravels. I mean, it had like well, it was a landfill really, and it has also a small mud layer. And I will present some results from a preload embankment, slightly narrower, but also height, and that was risen very fast. And here, those are the, you see that there's quite a lot of variation between the different locations within the embankment. Those are two plates, and the, well, this is the embankment height, and this is the prediction. The prediction is almost double than what the within stand load. It's almost double that what the plates had been measuring, but then this is a prediction as well, and I'm not showing here because I didn't want to put three graphs on the same slide, but looking at some surviving data from one of the extensometers, what has appeared now is that we were way too conservative in our estimate of what was the fill response, but we didn't have any data because the dilatometer didn't work there. So to conclude, well, I want to thank Professor Marchetti, because thanks to his invention and to many people in this room that have worked on this apparatus, well, we have been able to solve what at the beginning looked like a rather tough problem. And from the still provisional comparison results, I will say that for the standard profile, sand, silts, clay, perfect match. For non-standard profiles, well, it's more tricky. Thank you very much for your attention.